Good evening.
Good evening. Good evening.
Yeah, good evening. So, welcome to the live interaction session. So, we will wait for some more participants to join us. So, please stay tuned. We will start in another 5 minutes. We'll start at 6:10 sharp.
Okay, sir. No problem.
Yeah,
Okay, no problem.
thank you. Hello, good evening, and welcome back once again. So,
Good evening.
Yeah,
Yes,
yeah.
good evening.
Today there is one participant. Sir, I think we have not had the opportunity. Presently, we are in week 7 of the live interaction session. Would you like to introduce yourself? And since we are midway in the course, if you have any feedback, kindly let us know so that we can work towards improving the live interaction session going forward.
Okay.
Hello. Sir, would you like to introduce yourself?
My name is Mari Muthu from
Okay.
Chennai.
Okay.
Uh, I'm working private concern,
Okay. Okay.
and I'm doing my MTech structural part time in SRM University, Chennai.
Okay. Okay. That's very nice to know, sir. How you're finding the course so far? The weekly lectures and the assignments and the live interaction session.
Yeah, continuously following, but now I'm attending six. That is Thursday six. One more person taking, no sir.
Yes. 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 Yeah.
That
Yes, sir. I
okay,
think
you shifted
Tuesday.
to Thursday to Saturday. Okay, it's helpful to attend the one more section.
Yeah. Yeah. Yes, sir. So that is the intention actually. The
Hmm.
live interaction sessions are designed in such a way so as to uh, help you to understand the concepts and solve the assignment problem and eventually the exam questions in a better way. So we are here for you. And yeah, so thank you for joining. We are going to start the today's session.
Yeah. Oh, sure, sure, sure.
So I hope that my screen is visible.
Visibles, visibles.
Okay, okay. Thank you. So again, I welcome you all to the week 7 of the live interaction session. And the name of the course is Advanced Reinforced Concrete Design. And the course instructor is Professor Surya Prakash. And presently, we are in week 7 of this live interaction session. So we have completed 6 live sessions so far. So we can say that we are midway in this 12 weeks NPTEL course. And this session is presented by me. My name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi. And I welcome you all to this course. And so this will be the agenda for today's session. So as we have been doing or following for the past 6 weeks, what we're going to do is uh, in week 6 of this course, week 7 of this course, we are completing the module 5, that is the behavior and design of reinforced concrete members under flexure. So in module 5.5, we considered the flexural design aspects using IS code, where we considered the design aspects of singly reinforced cross section. So up to module 5.4, we had considered the analysis aspects. So now we will see how we can adapt that to the design aspects and what will be the difference with when it comes to the analysis and the design aspect of the singly reinforced cross section with respect to the original material properties and the Indian Standard Code. And then we are going to consider this concept of limiting neutral axis depth. So limiting neutral axis depth is going to help us in the analysis and the design of the reinforced concrete section as per the IS code. Okay, so as you might be aware, in week 1, we had considered that there are certain partial safety factors which we need to consider when we are following the analysis of the design as per the Indian Standard Code. So we'll be looking at those partial safety factors today. And then we are going to discuss the design aspects of doubly reinforced cross section. And then we are going to, then we saw the design aspects of the flange cross section. And then in module 5.6, we have considered the design examples from singly reinforced and the doubly reinforced beam. And so in this week's lecture, Professor Surya Prakash sir, he has started with module 6 also, where we considered the analysis and design aspects of reinforced concrete members in shear. But since it was a very small aspect, I've decided to take it up in the in the next live interaction session. But if there is any doubt, feel free to post it in the discussion group. I'll be happy to address that with whatever doubts or concern you might be having. So in the live interaction 8, we are going to be taking up the analysis and design of reinforced concrete members under shear as well as the torsion. So with that introduction, without any further delay, because we'll be discussing almost 17 questions in today's session. So without any further ado, let us start today's session. Again, this session is going to be a mix of the conceptual multiple choice question and the numerical multiple choice question. And I'll be here in helping you to solve the numerical problems and also understand the conceptual problems yeah, in a better way. So we'll start with the questions now. So the first question is, according to IS 456 2000, that is the code for reinforced concrete design. So what is the area of stress block for concrete in compression? That is the first part. And second part is, what is the depth of the resultant compressive force from the extreme compression fiber? So, so first we need to answer what is the area of the stress block for concrete in compression, and the second part is depth of the resultant compressive force from the extreme compression fiber. Okay, kindly take a few seconds and let me know what is the correct response. Okay, thank you for the answer. So basically, what we do in our class is that you can either unmute yourself and answer, and or else you can type in the chat box also. Both are acceptable. Okay, so we'll try to keep it.
Okay.
Yeah, yeah. We'll try to keep it
Answer
flexible.
A. Yeah.
Yeah, yeah, yeah. Thank you for your response. So we'll look at the answer. Okay. So actually you got close to the answer. I will explain what is the confusion. Maybe the way I put it, it might have been confusing, perhaps. So we'll look at the answer, sir. So, so what you are trying to, ask, or what is the what is being asked in the question is that first we need to determine the area of the stress block of the concrete in compression, so that the area of the concrete uh, stress block in compression is 0.36 FCK into XU, and the second part is the depth of the neutral axis, or the depth of the resultant compressive force, that is 0.42 XU. Okay, so if you consider the area of the stress block in compression, that is, if you take the overall average of this area, where the maximum here compressive force is 0.67 FCK, then the average is 0.36 FCK into XU. That is the area of the compressive stress block. And then the distance of the resultant compressive force, that is 0.42 XU. So option D is the correct response. So I hope that the answer is clear.
Yeah. Okay. Sir. Understood. Understood.
Yeah,
Right.
yeah, okay. Maybe it's the way that I framed it. It might have been confusing. But again, I will reiterate once again. The area of the stress block is 0.36 into FCK into XU, and the depth of the resultant compressive force is 0.XU from the extreme compressive fiber. So moving forward, in question 2, for a reinforced concrete cross section, the ratio of the limiting depth of the neutral axis to the effective depth, that is XU max by D, depends on which of the following factors. Okay. Select multiple options if necessary. Kindly take a few seconds and let me know what is the correct response. So what we are looking at here is the value of XU max by D. XU max by D depends on which of the following factors. It can be one factor or it can be multiple factors. It has been adopted from the lecture slides.
Yes, depth of the beam and grade of concrete both.
Okay. Okay. Thank you for the response. So we look at the answer here. So the correct answer is option D. So we look at what is the rationale behind this. So basically, this is adopted from the lecture slides. So we see that essentially uh, to determine the value of XU max by D, the ratio of the limiting neutral axis depth to the effective depth, that depends on this particular equation, that is 0.0035 divided by 0.87 Fy by ES plus 0.0055. Okay, so what we will do is we need to substitute the different grades of steel. So when we substitute 250 or 415 or 500, we obtain the different values of XU max by D corresponding to the grade of concrete. So once we get this ratio XU max by D, so then we can proceed to determine uh, the depth of the neutral axis, the depth of the limiting depth of the neutral axis accordingly. So what we were looking for is the correct answer is option D only, that is the grade of reinforcing steel. So the ratio of XU max by D essentially depends upon the grade of steel only. Okay, and then the modulus of elasticity ES is pretty much the same for any grade of steel, that is 2 into 10 to the power 5 megapascal. Okay, so I'd like to reiterate that we were looking for option D. So
Okay.
yeah, moving forward. So question 3 is, when the grade of reinforcing steel increases, what happens to the ratio of the neutral axis to the effective depth for RCB? And assume that all the other parameters remain the same. Okay, kindly take a few seconds and let me know what is the correct response. So I'll give a hint that this reinforcing steel is the reinforcing steel in tension. So if we use FE 500 instead of FE 415, what will be the implications on the depth of neutral axis? Sorry, the ratio XU by D. So that is what we are trying to understand.
It is a decrease in, so XU by D is decreasing the
Yeah, yeah.
increase in the
Okay, okay. Yeah. Thank you
state.
for the response. Yes, thank you for the response. Uh, so as you uh, absolutely, as you pointed out, the value of XU by D decreases with the grade of reinforcing steel. So the the concept behind this question is that, so when we increase the grade of concrete, that is when we increase the grade of concrete from when we increase the grade of reinforcing steel from Fe415 to Fe500. So we need to look at the tensile force in the rebar. Okay. So when we use a higher grade of reinforcing steel, automatically the um, automatically what happens is that, excuse me, there's something came up. I'm sorry for the delay. Actually, something came up, so I had to attend that. Basically, there are two
No
ways of,
problem.
yeah, yeah. So there are two ways of answering this question. So one thing is that, like, we can look at the implication of increasing the grade of reinforcing steel on the XU by D ratio. So here we can see that as the grade of steel increases, the XU max by D it decreases. Okay, so that is one way. And the other way of looking at it is that, so when we increase the grade of reinforcing steel, okay, so what happens is that the area of steel decreases, okay, or yeah, the area of steel may decrease, okay. So what happens is that the XU value also it decreases in order to balance this tensile reinforcement. The XU by D ratio also decreases, okay. So using that, one is the using this equation and other is the physical explanation based on the mechanics, right? That we can say that the when we are increasing the grade of reinforcing steel, the ratio of the neutral axis decreases. Okay. So moving forward, question 4. According to IS 456-2000, a reinforced concrete beam is typically designed as which type of cross section and what is the corresponding failure report?
Yes, sir. Under reinforcement section, tension control failure.
Yeah. Thank you for the response. So as you rightly mentioned, option F is the correct response because whenever we are designing a reinforced concrete beam, whether it is a singly reinforced beam or a doubly reinforced beam, whether it is singly reinforced beam or a doubly reinforced beam, Okay, we are going to design it as a under info section, and we are going to make sure that it is a tension control failure, because whenever it is a compression control failure, whenever it is a compression control, it tends to be brittle, and it will fail without no sufficient deflection. On the other hand, when the failure is tension controlled, so it tends to be ductile. So what we mean by ductile is that we had looked into the definition in the previous class also, that usually when we carry out a moment curvature analysis of a cross section, so there are two phases. So one is up to the yielding. Okay, so the value of moment increases uh, for a very short span of the curvature, and later on when the cross section has yielded, it tends to follow a plateau. Okay, so this is called as the yielding point, and the ductility is a measure of this ultimate curvature to the yield curvature. That is, ductility which is given by mu is phi u by phi y, where u represents the ultimate state and y represents the yielding state. So when it is a tension control failure, it is more ductile and it undergoes lot of deflection. It undergoes sufficient deflection, which gives us warning prior to the failure. Okay, we have seen in the previous live session and also the weekly lecture that generally the ductility is very limited for a compression control failure. On the other hand, for a tension control failure, it is quite significant, and it is very much preferred according to the IS code design. So the correct answer for this particular question is option F, that is a given reinforced concrete beam as per the IS code is designed as a under reinforced cross section with the tension control failure. So moving forward, yes. So we will ensure this under reinforced failure, and we are going to ensure that the XU is less than XU max. XU max is the limiting depth of the neutral axis, and XU is the actual depth of the neutral axis. We are going to discuss more about this in the upcoming numerical problems. So we'll move forward. So in question 5, we need to answer, in the analysis and design of reinforced concrete beams under flexure, what is the expression for term R? Okay, please take a few seconds and let me know what is the correct answer. So this term R is particularly used in the,
B, R equal to mu by FCK BD square.
okay, thank you for the response. So we look at the answer. Okay, it is option A actually. Uh, as per the design aids, that is SP16, 1980. So there are certain charts which are being provided in order to help us in the design of reinforced concrete cross section. So according to that, uh, we take the help of this R factor, and again this has been adopted from the lecture slide also. and we are going to discuss and show this R term in the SP16 design aids or the code as well. So we are going to design the cross section based on this R value. So from the perspective of the analysis and design of reinforced concrete members for flexure, this term R is mu by BT squared. Okay. So kindly note that, and we will proceed with the next question. So as you might have seen in the this week's lecture also, so once you obtain the value of R, there are two methods of determining the area of reinforcing steel. So we are going to look at that in little more detail very shortly. So essentially, what we need to note is that R is given by mu by BT squared. Okay. So we'll proceed to the next question. Yes. So we have a numerical example or a sample problem over here. So we have a beam which is having a width of 250 millimeter and the overall depth or capital D is 450 mm. The concrete has a characteristic strength of 30 MPa FCK and the beam is reinforced with 4 bars of 20 mm diameter and the grade of steel is 500 MPa. Okay, and it is reinforced only on the tension side. Assuming the moderate environmental conditions, that is, uh, I would say that it is a cover of 30 millimeter and 10 mm transverse reinforcement is being provided. What is the depth of the neutral axis as per IS 456 without considering the limiting depth? Okay, kindly take a few minutes and let me know what is the correct response. So I'm going to provide a hint over here. So what we are looking at basically is a reinforced concrete beam, which is reinforced only on the tension side. So based on the force equilibrium, we need to identify what is the depth of the neutral axis without considering the limiting depth. Okay. So for the material properties, we are going to consider the partial safety factors as per IS 456 2000. Okay. I don't know if we have the, okay, we have the cross section. We can start, drawing the stress block over here. And then we are going to equate the resultant compressive force and the tensile force. And then we are going to obtain the depth of the neutral axis. Okay. Yes. So let us assume that this is the depth of the neutral axis, right? X here. So as we have already looked earlier, the uh, resultant compressive force is 0.36 FCK into XU into B if you are considering the width of the cross section, and the resultant tensile force in the rebar is 0.87 Fy into AST. Okay, so now we know that for the equilibrium of the cross section, okay, we need to equate these two forces, that is Cc is equal to Ts, right? And we'll put the forces now. 0.36 FCK into B into XU is equal to 0.87 Fy into AST. So we can obtain the value of XU as 0.87 Fy into AST divided by 0.36 FCK into B. Okay. Kindly substitute these values and let me know what is the correct answer.
Two not 2.45.
Okay, yeah. Thank you for your response. So yes, so we're going to round it off to the first decimal point, and the depth of the neutral axis 202.25.5 millimeters. So option C is the correct response. Okay. So if we were considering the previous parts of the module, so if we just remember the analysis of the reinforced concrete beam, considering the material properties, we might have gone ahead with the depth of the neutral axis. So just out of curiosity, let us try to find out the ratio of XU by D. Okay, let us see what insights that is going to give us. Okay, so XU by D. Okay, and so we need to determine the effective depth. D is equal to total depth minus clear cover. Okay, clear cover is 30 millimeter, and then we have the stirrups, that is 10 millimeter, and then another uh, 10 millimeter, because we are going to consider half of the dia of the tensile reinforcement. So we have D is equal to 400 mm. Okay, so we have XU by D is 202.5 divided by 400. So that turns out to be how much? 0.506. But we know that we had looked in one of our previous slides that we have the limiting depth of the neutral axis, the ratio of the limiting depth of the neutral axis XU max by D, that too for grade FE 500 is 0.46. Okay, so that tells us that when we are considering the analysis of the design of the reinforced concrete beam as per the IS code, okay, we need to consider the limiting depth of the neutral axis, that is XU max by D. So whatever XU by D value that we get, if it is less than XU max by D corresponding to different grades of reinforcing steel, then we can go ahead and take the value of XU by D. But if the XU by D exceeds the value of XU max by D, then we need to consider the limiting neutral axis depth. Okay, so that is one of the measures that we take. One of the measures that we take in order to limit the moment of resistance for a for that factor of safety. Okay, so for the current question, without considering the limiting depth of neutral axis, the correct response is option C, 202.5. So we'll proceed to the next question.
Yeah, okay, sir.
Yeah. So the next question is, for the beam given in question 6, what is the limiting depth of the neutral axis? Okay. So as per IS 456, we have the value of XU max by D for different grades of reinforcing steel. So what should be the limiting depth of the neutral axis in order to determine the moment of resistance of the cross section? Okay, kindly take a few seconds and let me know what is the correct answer. So there are, in fact, there are two parts to this question. So the first part is we need to say what is the limiting depth of the neutral axis. That is the first part. The second part is what depth should be considered to determine the moment of resistance of the cross section.
Okay, sir. All right.
Yeah. So for the first part, let us calculate the value. That is 0.456 into 400, which gives us a value of 182.4 millimeter. Okay, for those like who are wondering how this value of XU max by D ratio is coming, I would like to.
IS 456, table number 4.2, sir.
Yeah, exactly, sir. So that is the standard reference, and it has been reiterated in the lecture slides also over here, that for different grades of reinforcing steel, we have different values of XU max by D, and it is essentially obtained from this uh, strain distribution across the cross section by using the similar triangles. So we can actually plug these values and see, when we plug different values of Fy, we get the limiting depth of neutral axis. That is the ratio of X max by D for Fe 500 is 0.456. Okay, and in order to determine the moment of resistance, what would be the value of Xu? So basically, we have two values of Xu. So in the previous question, as per the analysis, without considering the limiting value, we found out that it is 202.5, and presently we have 182.4. So we have 202.5 and 182.4. So out of this, which value we should consider for the analysis for the to determine the moment of resistance?
It's you max.
Yeah, absolutely. Yes. So you have answered correctly. So as we were discussing in the previous question also, so the IS code has inherently certain partial safety factors, and whenever the XU by D ratio is exceeding this XU max by D, then we need to consider the limiting value of XU max by D. Okay, and correspondingly we need to consider the lower value 182.4, and the correct answer for this particular question is option E. So we need to so the limiting depth is same as the depth that is being considered to determine the moment of resistance of the cross section. So option E is the correct response. So we'll move on to the next question.
Okay.
Yeah. Uh, so for the beam given in question 6, what would be the ultimate moment of resistance and curvature as per IS 456 2000? Okay. So for this beam, we need to determine the ultimate moment of resistance and the curvature as per the IS code. Okay. Kindly take a few minutes and let me know what is the correct response. I will also start solving the problem with you.
Moment is 165.6 kilometers.
Okay, you were able to solve it, sir? Like you were able to obtain the
I
answer?
used this one 0.136 into FCK B into D square, that formula, mu limit.
Okay, okay, okay. That's great. We'll have a look at the answer now. I'm sorry, can you please tell me what is the answer that you got once again?
Uh, that is 165.33 kilonewton meter
165. Okay, 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 okay. Thank you.
moment.
Yeah, I will solve it now. Yes. Okay. So let us, start solving this problem. So I'm going to solve it probably over here only so that both the question and the solution is at one place. So to solve this problem, that is to determine the ultimate moment of resistance as per the IS code, we are going to refer to Annex G, Annex G of IS 456, Annex G of IS 456. Okay, and we have already established that the XU max by D. So whatever XU by D that we need to consider to determine the moment of resistance, that has to be XU max by D. And for FE 500 grade, we know that the value of XU max by D is 0.46. So we are rounding off to the second decimal place. So as per this annexure G, we have the limiting moment of resistance, that is mu lim, as 0.36 XU max by D into 1 minus 0.42 XU max by D into BD square into FCK. Okay, so let us start plugging the values and we'll find out what is the answer. 0.36 into 0.46 into 1 minus 0.42 into 0.46 into B would be 250 into 400 square into 30. Okay, so based on this, I got a value of 160.33. So I'm getting the correct answer is option D. Uh,
Okay, sir. Got it.
yeah. Okay, sir. So we can actually solve using the other formula also that you mentioned. Uh, Let me just open up the module. Sir, can you tell me what is the slide number that you were referring? We can just cross-check with that formula also.
Couldn't remember that the TMU limit into 0.138 FCK B into D square.
Okay. Okay. MU limit is 0.138 FCK BD square. Is it correct?
Yes, yes, sir, yes.
Okay. And does it correspond to FE 500 500 grade?
So FE415.
Okay. So we need to consider that it is for FE 500, the current problem. So I think the the equation might be slightly different for uh, FE 500, I think. So I will get back to you, sir. Like I will, check what is the equation for FE 415 and 500. What is that? And anyway, the safe thing to do is to follow the IS code. Okay.
Sure, sir. I will keep an eye
Yeah,
for
yeah.
fine.
So yeah. I'll clarify that for you later on. Probably in the discussion group, I'll let you know. Uh, yeah, so the safe option for us, to use this IS code formula, which is, well established. And yeah, I will look for that maybe in IS code or I doubt it is there in the IS code, but maybe in SP16 it might be there. I'll look out and I will let you know. So the correct answer is option D, 160.33. And while we are at it, let us find out the value of curvature also. So we'll box it over here. And the curvature phi is epsilon c by xu, right? And epsilon c is 0.0035 divided by xu is 182.4. Okay. Let us find out the value. So which is giving me a value of 19.2.
19.02
Yeah,
into 10 power
19.
minus 5.
Yeah, absolutely. So option B is the correct response. So we'll proceed to the next question now. So we have evaluated the moment capacity and the curvature as per the IS code. Now for this question, we need to determine the ultimate moment capacity and the curvature corresponding to the actual material properties. Okay. Kindly take a few seconds and let me know what is the correct answer. I will also be, I will also start solving the problem along with you. Um, so we need to establish the equilibrium of the cross section. That is CC is equal to PS, right? And we know that the value of CC is alpha 1 F prime C into beta 1 into X into B. Okay. And yeah, we know that TS would be Fs into AST. So how do we find out? So for this, we know that we need to determine the depth of the neutral axis, that is X, by trial and error method. So we'll go to the Excel sheet and try to solve it using that. Okay. So I hope that my Excel sheet is visible.
Yes, sir. Visible. Visible.
Yeah, yeah. So we'll start substituting all the values. The width is 250, depth is 450, and the effective depth is 400, and the area of steel is 1256.64, and it will calculate the percentage of tension steel automatically. Then AC is 0, no reinforcement on the compression side. D prime we can leave it, and F prime C. So basically the characteristic strength is very much similar to F prime C value. So I'm going to put it as 30, and epsilon prime C, that is strain corresponding to the peak stress, that is 0.002, and Fy is 500. So we know that for the strain in concrete, when the strain in concrete is 0.0035, so this Excel sheet automatically calculates the value of beta 1 and alpha 1. So alpha 1 is 0.81 and beta 1 is zero point 0.9. So we'll write down those values. Alpha 1 is 0.81 and beta 1 is zero point 0.9. So we have already solved several problems in order to calculate these stress block parameters. So I'm going to skip that for the time being, right? And let us find out the depth of the neutral axis by trial and error, which is going to satisfy the force equilibrium. Okay. So we need to balance this TS and the CC. So please ignore the value of CS because there is zero compression steel. So presently the compressive force is higher. So we need to reduce the value of X. So we'll try for 165. We need to reduce it further, 160, 150, reduce it further, 140, reduce it further, 130, 120, 115. Yeah, so we are getting close to that value. So we'll try for a value of 114.8 maybe. Okay, 114.9. Yeah, I think now it looks good. So uh, the tensile force is 628.3 and the compressive force is 628.4. So that is acceptable. So X is 114.9. So X is equal to 114.9 millimeter. Okay. So let us solve the problem by using the equations, right? So we have established the compressive force and the tensile force. Now the value of M is Cc into D minus beta 1 into X divided by 2. Okay. So, okay. First we need to find out the value of Cc, right? So Cc is alpha 1 is 0.81 into F prime C is 30 beta 1 is zero point 0.9 and x is 114.9 into b is 250. So can you please tell me what is the value of CC that we are getting?
628.21 kilometers.
Yeah. Thank you so much. I think if we look at the Excel sheet also, we are getting the same value. That is 628 point, yeah, 4. Getting 628.2. Let's write that 628.2 kilonewton. Sorry for that. Yeah, 628.2. 628.2 into 10 to the power 3 into 400 minus beta 1 is zero point 0.9 into 114.9 divided by 2. Sorry for that. Writing in a small font. I had thought of adjusting this in
No
this
problem.
slide itself. So can you please calculate and tell me what is the moment capacity?
Two one eight, 218.8 kilometers.
Yeah. Thank you so much. And absolutely. So even I too got the same value. So option B seems to be providing the correct answer. So this is the moment capacity as per the uh, material properties. Okay. So as we can see over here, so there is quite considerable margin when we're calculating the moment capacity. So if we consider this particular cross section, okay, so for this cross section, considering the actual material property, we obtain the moment of resistance as close to 220 kilonewton meter, and as per the IS code it is 160, and the curvature is 30.5 as per the actual material property, and the IS code is 19. So uh, basically I think we can say that broadly there are two parameters which have affected this difference in results. So two parameters. So I think the first parameter would be the limiting neutral axis depth. Let me write XU. So limiting XU. So because of limiting the value of XU, we are limiting uh, the compressive stress block as per the IS code. And then the balancing tensile force is also less, as a result of which we get very conservative value of the moment of resistance. And secondly, the partial safety factors. So partial safety factor. So when we are considering the IS code, we are going to consider CC as 0.36 FCK into XU. So that is the value. But when we consider the actual material properties, CC is equal to alpha 1 F prime C into beta 1 into X. So if we consider alpha 1 as 0.81 and beta 1 as zero point 0.9, so this will become let me just calculate. Zero point 0.9 into 0.81, that is 0.73. That is 0.73 FCK into XU. So we can see that the when we are considering the actual material property, the resultant compressive force is almost twice as this IS code value, which results in higher values of mu and the phi. Okay, so these are the two parameters, which is the reason behind the enhanced values of moment of resistance and the curvature for the when we are considering the material property. Okay, so with that discussion, we can proceed to the next question, because we have another 8 questions, I think, for today. So without any further delay, we'll proceed to the next question. So consider a beam of width 300 millimeter and overall depth of 500 millimeter, and characteristic strength is 40 MPa. If the beam is subjected to 250 kilonewton meter, will it be designed as a singly reinforced beam or a doubly reinforced beam? Okay, so please assume HYSD 500 bars are used and 10 millimeter stirrups are provided, and take moderator environmental exposure conditions. Okay, kindly take a few seconds and let me know what is the answer. Uh, so looking at the problem, can you please tell me what is the approach to solve this problem? So broadly, if you could tell me uh, the broad approach, that would be nice moving forward. Okay, this is the hint. So this is the ultimate moment that the beam is subjected to. Let us call it as MD, right? So if the value of MD is less than MU limit, which is calculated as per the annexure G, then we can design it as a singly reinforced cross section. Okay. On the other hand, if this MD MD is greater than MU limit, so MDD corresponds to the demand. So if the demand is greater than the MU limit, okay, let us say that if MU limit comes out to be 200, 250, 250 is greater than 200, then we need to design it as a doubly reinforced cross section. Okay. So with that introduction, I think we can start solving the problem. Oh,
Yeah, okay, understood.
yeah,
Understood.
yeah. I think by mistake I showed the answer also. So anyway, we'll solve the problem now, and we'll see what is the value of mu limit we are getting as per the annexure G. Right. Okay.
This one 0.36 XU max by D on this formula.
Yeah, yeah, exactly. Yes, yes. Yeah, so we have here. Mhm. So I will solve the problem. Yeah, I'll write down the data. FCK is 40 MPa, right? FCK is 40 MPa, and then Fy is 500 MPa, and we know that correspondingly the XU by D, or the XU max by D, because we are finding the MU limit, that is 0.46. So we know that as per annexure G of IS 456, we know that MU lim into 1 minus 0.42 XU max by D BD square into FCK, right? So we'll start solving, substituting the values. The limiting moment of resistance 0.36 into 0.46 into 1 minus 0.42 into 0.46 into 300 into 450 square into 40. So what is the MU limit we are getting? And what is the MD that we have? That is the design moment. I'm getting a value of 324.66. So I'm getting a value of 324.66 kilonewton meter, right? And the design moment is 250 kilonewton meter.
Yeah, it's less than
Yeah, yeah,
250 kilonewton. That's what it's a single reinforcement.
yeah, right, sir. Exactly, exactly. So we have the demand. The demand is less than the ultimate capacity. Okay. So that is 250 is less than 370, sorry, 325.
324.66.
Yeah, yeah. So yeah, thank you for confirming that. And as a result of which we can design the beam as a single reinforced cross section. Now let us go ahead and actually design this beam as per the IS code. Yeah, so if the design bending moment, I'm going to call it as MU. MU for the beam is given as 250 kilonewton meter. Determine the area of steel reinforcement required. Okay, so if you look at this week's lecture, so basically there are two methods are given in order to calculate the reinforcing steel. Okay, so there are two methods. So kindly calculate the area of steel required using the first method, that is by calculating the neutral axis depth from the moment demand. Okay, so as a hint, let me go back to the this week's lecture slide, okay, to help you locate where the equations are. Yes, so I'm referring to this slide number 12. So we need to uh, obtain, calculate the value of R is equal to mu by BD square. So when we have the value of R, determine the ratio of XU by D, where XU is the depth of the neutral axis. And once we have the value of XU by D, uh, calculate the value of ASD. Okay, please follow this method one. Okay, I'm going to solve it. We're going to solve it simultaneously and let me know what is the correct answer. Okay. Slide number 12 from module 5.5.
Yeah, okay.
So we are going to obtain the value of AST using these two methods and see whether there is any difference. There should not be any difference, ideally, right? So, okay. So basically, I think it's a three-step procedure that we are following over here. So the first step is find out the value of R. Okay. So R, as we can see over here, is given by mu by bd square. Mu by bd square. That is, mu is 250 into 10 to the power 6. Express all these in terms of Newton and millimeter. And B is 300 by 450 square. I'm getting the value of R as 4.1152. Yeah. Thank you. Thank you for confirming that. We're going to uh, take it up to the fourth decimal place in order to ensure accuracy in the calculations. And then we need to determine the ratio of XU by D, right? XU by D is 1.2 into 1 minus square root of 1 minus 4.6 into 4.1152 divided by FCK. The value of FCK is 40, if I'm not mistaken, which gives us the value of, so XU by D, I got a value of 0.3291. So one of the checks that I would recommend to all the students and participants is that, as we have seen earlier, this XU by D, it can exceed the XU limit, XU max by D for the analysis using the material properties. But whenever we are designing as per the IS code, it should never go beyond the XU max by D values. Okay. So for the current problem where we are using Fe500 steel, so for Fe500, this particular value always has to be less than equal to 0.46. Okay. So this is one check that the participants can follow while solving these problems. So we obtain the value of XU by D, then we can substitute that value in this equation. Mu is 250 into 10 to the power 6 divided by 0.87 into 500 into D is 450 into 1 minus 0.42 into uh, XU by D is 0.329. Can you please let me know what is the AST that we are getting? So as per this,
1481 mm space. Huh?
yeah. Thank you, sir. Thank you for confirming. And as per this first method of calculating the neutral axis depth from the moment demand, we get AST required as 1481.96 mm square. Okay. So option C seems to give us the correct response. So having found out the AST of the first method, let us proceed to take up the next problem. So in the next problem, we are going to use the direct calculation method. Okay, so I will show the hint once again. So here we have already found out the value of AST from method 1. So in the direct calculation method, we are going to obtain the AST directly. So first step is we are going to find out the value of R. We already know the value of R, and then by using this equation, we are going to find out the value of PT, and from PT we are going to obtain the value of AST. Okay. So first step is find out R, which you already know, then find out the value of PT, and from PT we'll find out the value of AST. Okay. So we can start solving the problem together. Okay. So we already know from the previous. Okay. So from the previous part of the question, we know that R is equal to
4.11.
okay, yeah, thank you for that. Going to write it here. So the first step is R is equal to mu by bd square, that is 4.1152. So let us proceed to the second step, that is pt by 100 is equal to fck. Okay, let me write down the equation once again for better clarity. Fck by 2fy into 1 minus square root of 1 minus 4.6 r by fck. Okay, we'll substitute the values and determine what is the value of pt that we are going to get. Right, so pt by 100 is equal to fck is 40. Yep, 40 by 2 into 500 into 1 minus square root of 1 minus 4.6 into 4.1152 divided by 40. So when we solve this, can you, okay, let me write down the value of pt.
0.019.
I'm getting 1.09.
In the percentages.
No, sir, like you have to take multiply it by 100, obtain just value of pt. So please check and let me know if you're getting this.
Yeah, yes, sir. We got it.
1.097. Yes, thank you. Okay, and the third step is we need to find out the value of AST. So PT 1.097 into 300, that 300 by 450.
Yes, sir. 1,480.95.
Yeah, yeah. Thank you. Thank you for the response. And I'm getting 1480. So I think option D is providing us the closest answer, the correct answer. So we'll go back and check what is the value of A that we got previously. So it is 148, 1482, 1480. So 1480.8, which is, quite close. So in your assignments or in your exams, so since we have validated both these two approaches in order to obtain the value of AST, so please feel free to use either of them, and both of them will get you can obtain the same answers. So with that, we can proceed to the next problem. So I think for today we have another 5 questions and another half an hour. So we are doing well time wise. So it is a conceptual question. I'm going to read out the question and then the options. Okay. Uh, which among the following reasons is not a reason? Which among the following is not a reason for providing compression reinforcement in the flexural members? So we know the reasons for providing the compression reinforcement. In this question, we need to identify which among the following statements is not a reason for providing the compression reinforcement. Okay. So you can select multiple options if necessary. So the first statement is transferring compressive stresses from concrete to steel. Second is support to the stirrups, providing support to the stirrups. Third is reducing the creep of concrete. Fourth is lesser deflection under sustained loads. Fifth is changing the failure mode from tension to compression. The sixth statement is increasing the moment capacity and the curvature capacity. Okay, please take a few seconds and let me know what is the correct response. So one hint is that there is only one correct option.
D and E. D and E, sir. Lesser deflection under the sustainable load,
Okay,
changing the failure mode from the tension to
okay, okay. Thank you for that response. So the one hint that I can give for this particular question is that there was only one correct answer, and I would like to clarify that option C and option D are essentially the same, sir. Because what is the definition of creep? Creep is nothing but deflection under sustained loads. So when we are providing the compression reinforcement, we are reducing creep. So out of these options, option E is the correct answer. So yes. So out of the 6 options, compression reinforcement helps in transferring compressive stresses from concrete to steel. That is correct. It provides support to the stirrups. That is also correct. It reduces the creep in concrete. So option C and D, both statements are correct, right? And compression reinforcement helps in increasing the moment and curvature capacity. So option E is the wrong statement, and it is not the reason for providing the compression steel. Um, so we'll move on to the next question, right? Yes, so it reduces creep and the compression steel, and it also uh, ensures that there is less sustained load deflection. Right? Moving on. So we are coming back to the numerical problem. Consider a beam of width 300 millimeter and overall depth of 500 millimeter. And the concrete has FCK of 40 MPa. If the beam is subjected to a bending moment of 600 kilonewton meter, what is the area of steel required in the compression zone? Okay. Kindly take a few seconds and let me know what is the correct response. I will also start solving the problem with you. So essentially, it is a continuation of one of our previous problems. So we can actually take the help of that in order to solve this particular problem. I'm going to tell you where exactly the link is. Okay. Please. Uh, Let me draw the cross section. Okay. Very quickly. So it's having a width of 300 millimeter and the depth is 500. 300 and the depth is 500. Let's take the effective cover as 50 millimeter. Effective depth is 450, right? And FCK is 40 MPa and Fy is 500 MPa. Okay, so the question that we are presently discussing is the same as the question we have discussed in question 10. So the width is 300 millimeter. Sorry, I'll show the laser point. Width is 300 mm, depth is 500 mm, and the FCK is 40 MPa, and then the HYSD bars are uh, Fy is equal to 500, and the effective cover is again 50 millimeter. So we can make use of the mu limiting value in order to uh, obtain the answer for our current problem. So please note that mu limit is 324.66 kilonewton meter. Okay, 324.666 kilonewton meter. Now, let us see using this data how we can solve our current problem. We are presently in question 14. So, in order to obtain the compression reinforcement, we use this value mu minus mu limit is equal to FSC into ASC into D minus D prime. Okay. Uh, I think we have all the data that is required in order to obtain this value, right? Yeah, so we need to let us have a look at this, equation for a second now, for a moment now, right? And let us try to see what we have and what we need, what is the extra data that we need to solve this problem. Okay, so we have the value of mu is 600 kilonewton meter, and mu limit is 324.66. It is 600, right? We need to find out the value of FSC, and FSC is basically a function of epsilon SC, that is the strain in reinforcing steel. Okay, from finding out the value of strain in reinforcing steel in compression, we can obtain the value of FSC, and ASC is to be determined. Okay, and we know the value of D and D prime. D is 450 and D prime is 50 millimeter. Okay, let us proceed to find out the value of FSC now, right? I'll write down the equation here once again. Mu minus mu limit is equal to FSC into ASC into d minus d prime. Okay. So in order to obtain the value of FSE, we need to obtain that value from the strain. So how we are going to obtain the value of strain? So let me draw the strain distribution across the depth of the cross section. So this is the value of epsilon SC, epsilon SC, strain in the compression steel. And here this is the value of epsilon C. Okay. So from similar triangles, okay, if we consider this as the neutral axis depth, that is XU, if we consider this as XU, from similar triangles we have epsilon C by X is equal to epsilon SC by X minus D prime. Okay. I'm going to find substitute all the values and we'll see. And what is the value of X presently? Yeah. We will solve the problem, right? Okay. So we have X is equal to, sorry about that. I was just trying to locate where I had written the value of X, right? So we know that X is equal to 0.46 into D, right? 46 into D, that is 0.46 into 450. Okay. So what is the value of X?
207.
Okay, thank you. Thank you, sir. So X is 207, right? Let us substitute those values and
Divided by 207 into 207
yeah,
minus 50.
minus 50. Epsilon SC is,
0.0026.
yeah, exactly.
10 into
Yeah, right, sir. So I'm going to express this so that, we can calculate it little more with little slightly more accuracy. Okay, so from the interpolation, we have these strain values. Okay, so corresponding to 0.00226, we have 391.3, and 0.002777, we have 413.0. So the value of stress lies somewhere in between. So from the linear interpolation, we obtain FSC is equal to, um, shall I write the equation for linear interpolation, how we are finding it out? Sir, are you aware of the equation for linear interpolation?
Yeah, yeah, yes, sir, yes.
Okay, okay. So basically, this is, uh, 391.3 plus this, 413.0 minus 391.3 divided by this difference in the strain, that is 0.00277 minus 0.00226 into the change in the strain, that is 0.00265 minus 0.00226. So this is the equation to for the linear interpolation. So from that we obtain FSC as, so I'm getting this F408.1. So you may kindly verify that value, right? So it lies in this range, right? So let me go ahead and solve. I'm going to take different color to distinguish this for better contrast now. So we have, let us substitute the values, 600. So we are basically solving this equation now. 600 minus uh, 324.6, right? Yeah, 3, sorry, 3, 324.6 into 10 to the power 6 is equal to FSA. We know that it is 408.1 into ASC into D minus D prime, that is 450 minus 50, that is 400. So once we solve this equation, we get the value of ASC as, yeah, it is 1687.6, 1687.6 mm square.
One
Okay.
six seven.
Yeah. Thank you so much for confirming, right? So I think option D is giving us uh, the correct value. So by using this equation and then by linear interpolation, they can obtain the strain, the stress corresponding to the strain in the compression steel. So by using this equation, we were able to obtain the area of steel in the compression zone. Okay. So we'll proceed to the next question now, right? So for the beam given in question 14, what is the area of steel required in the tension zone? Okay. So we can start solving it, the problem now, right? So
You can use MU limit formula, sir.
for which one, sir? This one?
Ah,
Yeah, sure. We can use that. Okay. So please wait for a moment. I'm going to, solve it using the shortcut method. Okay. It
yeah,
is
okay, sir.
based on
Okay.
what sir has solved in the class, and you can use the same in your assignment as well as the exam also. Okay. So, uh, right. So we have, from the lecture slides, we can see that for the tension reinforcement, uh, you can use this method where, the value of PT limb by 100 into Fy by Fck, this can be simplified for as certain value depending on the grade of steel. Okay. So this, I'm going to start by this. AST can be divided into two components, that is AST1 and AST2. So here AST1 is the area of steel corresponding to a singly reinforced balanced cross section. Okay, singly reinforced balanced cross section. And this AST2 is to obtain the equilibrium for the compression steel. Equilibrium for compression reinforcement. Okay, so now let us see how we can obtain each of these values. Okay, I'm going to start with AST1, right? So yeah, I'm going to take a different color for a better understanding here. Okay, we have AST limb is equal to PT limb by 100 into Fy by Fck. Okay, this has to be 0.189 corresponding to Fe 500. Okay, so let us solve this and see what we are going to get, right? So PT limb is equal to 0.189 into 100 into FCK is 40, Fy is 500. So when I simplify this, I'm getting a value of 1.512. So the PT limit value is 1.512. Further, this PT limit is nothing but AST limit divided by BD into 100. Okay, so AST limit is equal to PT, right? PT is 1.512 into what is B? 300. D is 450 divided by 100. Can you please tell me what is the value of AST limit?
2045.25 mm square.
Yeah. Thank you. Thank you for the response. I'm getting 2041. So this is, we have AST1, that is the, for a singly reinforced beam, what is the balanced area of steel? So now we need to obtain AST2 in order to balance the compression reinforcement. So let us do that now. Okay, because of the lack of space, I'm going to do it here. So if we consider the cross section, then we need to balance this compression, the effective compression force in the compression steel and the AST2, right? Let me write it as TS2, that is FSC into ASC is equal to 0.87 Fy into AST2. Okay, so we have we know the value of FSC over here, or let me simplify that for in terms of the AST. AST2 is equal to FSC into ASC divided by 0.87 Fy. Okay, so if you're wondering why we are not considering this 0.87 Fy, that is already being considered in this particular chart. Okay, so in this particular chart we already considered that uh, uh, partial safety factor. So from this we know that FAC is 408.1 and AAC is 1687.6. Let me plug those values in this equation. FAC is 408.1 into AAC is 1687.6 divided by 0.87 into 500, which gives us the value of AST2 as 1582.42 mm square. So as I said earlier, in order to obtain the total AST, AST is equal to AST1 plus AST2, right? Let me take a different color now. Right, 82.42. What was AST1? AST1 was 2041.2. So the total AST turns out to be 36,
3624.2.
yeah, 3624 mm square. So option C is the correct response. Thank you for confirming the answer. So in this way, once we determine the value of ASC, um, once we determine the value of ASC, we can obtain the value of AST. So as I told earlier, AST comprises of two components. The first component is the balanced steel, the steel corresponding to a singly reinforced balanced cross section AST1, and for different value for different grades of steel, different grades of steel, we can obtain the value of AST by this procedure, and then AST2 is obtained by equating with the force in the compression steel. So from that, we can obtain the value of AST1 and AST2, add them together, we obtain the value of AST, and finally we get this the answer. Okay. So we have another two questions. Okay. So I think we'll be taking uh, another maybe 10 minutes beyond. I hope that that is fine.
Okay, sir, no problem.
Okay. Thank you. So we have another two questions. So we'll proceed further. Okay. So yes, I think this we have an opportunity to solve it using the Excel sheets. Okay. And I'm going to start reading the data now, and then we can start solving the problem together. Okay, so we have a reinforced concrete beam of dimensions 300 by 500 millimeter, and the value of FCK is 40 MPa. The beam is reinforced with 4% steel on the tension side and 2% on the compression side, and it is having an effective core of 50 millimeter on both the sides. What is the ultimate moment of resistance and curvature as per the IS code? Okay. So we need to determine the ultimate moment of resistance and curvature as per the IS code. Okay. So kindly take a few seconds and understand the data. Then we can start solving the problem simultaneously. Okay. So this because it is an analysis problem, we need to take the help of the Excel sheet uh, in order to solve this problem, right? So the basic difference between this analysis as per the IS code and analysis as per the uh, material properties, the actual material property is that the stress block parameters are different. Okay. As I was already explaining earlier, we are going to see it more in detail when we solve using the Excel sheet. Okay, so I think we already have the data over here. So we need to determine the moment of resistance and the curvature as per the IS code. Okay, and we can take the help of this stress strain data in order to solve the problem, right? So let me draw the strain distribution across the depth of the section. We have epsilon c is equal to 0.0035, and then we have epsilon sc, steel in compression. Then we have epsilon s, and here this is the depth of the neutral axis, that is x. Okay, and now we have this, the stress block diagram. This is the tension in reinforcing steel, right? And then this is the depth of neutral axis. So it follows partly rectangular and partly parabolic um, profile. This is um, resultant compressive force in the concrete block, and here we have the compression from the steel. Okay, then in order to obtain the moment of resistance, we need to take the value of epsilon c as 0.0035. Now we need to select the value of x so that there is equilibrium. There is equilibrium of the cross section. Equilibrium of forces in the cross section. So how do we achieve that equilibrium? I'm going to write it here. So basically the two compressive forces should be equal to the tensile force, right? And this Cc is, please note that we are doing the analysis as per the IS code, that is 0.36 FCK into B into XU plus, that is Cc, plus FSC into ASC, right, is equal to uh, FST into AST. And we are going to obtain these values based on the strains that we have. Okay. Now, it is not possible, to straight away take a value of x and check for the equilibrium. So for that, we are going to take the help of the Excel sheet right now. Okay. So actually this Excel sheet, it has two components, right? So this is based on the material properties, and this is based on the IS code. And I've taken this stress strain curve from the SP60. So let us plug all the values and see, right? And before that, let us calculate the area of steel in the compression and tension, right? Sorry, I should have done that earlier. So now we have AST and ASC, right? AST is 0.04 into BD, capital D, that is 300 into 500, right? And this is 0.02 into 300 into 500, right? So we get the value of 6,000.
6,000 mm.
Yeah, thank you. And this is 3,000 mm square, right? This is AST and this is ASC. So we'll go back to the Excel sheet. 300 by 500 and effective depth is 450, and then A stays 3000, and it will calculate the percentage steel automatically. Then the compression steel is 3000, then the corresponding percentage is 2%. Then D prime is 50 mm, FCK is 40 MPa, as we have seen. And then the strain corresponding to the peak stress is 0.002. Then Fy is 500 MPa, and there is no actual force. And then corresponding to a strain of 0.0035. Okay, so in fact, this X is already balanced because I already used this um, while creating the problem for today's session. So we can see that for a value of 265.4, the tensile force and the compressive force, both of them are equally balanced. Okay. So we'll do some hand calculation and we'll find out, how it is getting balanced over here. Okay. So X is 265.4, 265.4 mm. Okay. Now, yes, let us check, what is the value of xu by d, just out of curiosity. X by d, that is 265.4 divided by 450. Can you please tell what is the value?
0.5.
Yeah, yeah, thank you. So this 0.59, that is greater than 0.46, and still it is permissible because it's a doubly reinforced cross section. So once we have obtained the value of X, let us find out the value of in the compression steel, right? Now, from the stress block, we have epsilon C by X is equal to epsilon S T by D minus X. Okay, that is 0.0035 divided by X is, so we obtain epsilon ST as, so it is 0.00243. So correspondingly, the stress I'm going to we are going to obtain using the linear interpolation. It is between 391 and 430. That comes out to be 398.7 MPa. That is the value. That is the value of stress in the tensile reinforcement. Okay. AST. This is ASC. Okay. Now we'll find out the stress in the compression steel. Okay. Let's move on to the next slide. Right. I'm going to number the steps, side by side. Now we have done up to step 3. Next is step 4, right? Step 4 is, again, from similar triangles, we have epsilon C by X is equal to epsilon S C divided by X minus D prime, right? 0.0035 divided by X is 265.4 is equal to epsilon SC by 265.4 0.4 minus 50. So solving that, we get epsilon SC as 0.00284 or 5. Correspondingly, from the linear interpolation, 0.285, it has to be between these two values. Correspondingly, I get the value of FSE as 415.2 MPa. Now we have all the stress values obtained. Now we are going to check for the force equilibrium. Okay, I will check for the force equilibrium. Let us start with the compressive force in the steel, that is 0.36 FCK B into XU, that is 0.36 into 40 into 300 into how much? 265.4. And then CS is FSC into ASC, right? And we have ES is equal to FST into AST. Okay, now we have 415.2 into AAC is how much? 3000, I guess. And here FST is 398.7 into 6000. So CC, I'm getting it as 1146.5 kilonewton. And then CS is 1245.6 kilonewton. And then TS is 2392.1 kilonewton, right? So from this, we are able to obtain the equilibrium of the cross section. CS plus CC is equal to TS. Okay. So once we get the force equilibrium, we need to obtain the moment value. Now let us take the moment about the tensile reinforcement. That is M is equal to CC into D minus how much? D minus 0.42x plus CS into D minus D prime. Okay. You may kindly calculate the value and let me know what is the correct answer. That is 1146.5 into 10 to the power 3 into 450 minus 0.42 into x is 265.4 plus CS is 1245.6 into 10 to the power 3 into 400. So from this, I get the value of 886.4 kilonewton meter. Okay, you may please check it later on. And phi is, let me write it here. Phi is equal to epsilon c by x 0.0035 by 265. That gives me a value of 13.2 into 10 to the power minus 6 per millimeter. So m is 886 and phi is 13.2. Yes, so option D gives me the correct answer. I hope that you were able to obtain the answer, sir.
Yes, yes.
Okay, okay. So again, option D is the correct answer. So we'll finally proceed to the last question for the day. And then I'm not going to burden you any further. We are going to solve this using the Excel sheet. Okay. Um, So I know that the previous problem was a bit intensive. Um, no? So we're going to solve it using the Excel sheet now, right? So uh, do you have the comparison? No, not yet. Okay. So for the same problem, we need to obtain the ultimate moment of resistance and curvature using actual material properties. So we know, what is the difference between the actual material properties and the IS code, right? Let me write it just for better clarity. So we have the analysis of RC section. So the first is using the IS code, other is using the material properties. So when we are using the IS code, we have partial safety factors. On the other hand, material properties, they are based on the stress block parameters. Okay. Okay. So we can start solving it. Um, so we'll go back to this. Yes, we have, okay, this is 300. Width of the cross section is 300 and the depth is 500. Effective depth is 450 and AST is 6000 mm square and 4%, 3000. And then the percentage of compression steel is 2%. D prime is 50 mm. F prime C or FCK is 40. Then epsilon prime C is 0.002. Fi is 500. And the first step is we are going to assume the strain in concrete, that is 0.0035. And then we need to calculate for the force equilibrium in the cross section, that is Ts should be equal to Cc plus Cs. Okay. And we have the stress block parameters alpha 1 and beta 1 automatically calculated corresponding to the value of strain in concrete. Now we see that the value of Cc plus Cs is less than Ts. So we'll increase the value of um, the X or the neutral axis depth. Now I'm getting that corresponding to a value of 172.45. I'm able to achieve this equilibrium of the cross section where Cs plus Cc is equal to Ts, that is 3000 kilonewton, right? For X is equal to 172.45 millimeter. Okay. For X is equal to 172.45 millimeter, we're able to obtain the equilibrium, that is Cc plus Cs is equal to Ts. Now we can go ahead and find out the value of M, okay, using the actual material properties. M, taking moment about the tension reinforcement, that is Cc into d minus beta 1 into x by 2 plus Cs into d minus d prime. Okay, and phi is equal to epsilon c by x. So when we look at the Excel sheet, we get the values of M as 1158 and 20.3. 1158 and 20.3 into 10 to the power minus 6. So option C is the correct answer. Okay. So with that, we will conclude today's session. And if there is any questions, please feel free to, post it on the discussion portal. And in the next week, we're going to be taking up design for shear force and the torsional moment.
Okay, sir. Got it.
Okay.
So this Excel sheet can I get, sir? How can we get the Excel sheet?
Uh, so uh, there is some yeah, disturbance. Yeah, thank you for that. And sir, like you might be aware that there is one Excel sheet where all our recordings are available. So, NP. Okay, so this is the Excel sheet, data sheet where everything is available, right? So if you go to this Google Drive, so all my presentation slides are there. So I'm going to upload my Excel sheet here. So you can access that and you can use it for the solving the assignment problem in
Okay, sir.
the exam. Okay. Okay.
Thank you. Thank you,
Okay.
sir.
Thank you. Thank you. See you again next week.
Sure, sir. Thank you.
Yeah.
Thank
Yeah.
you.
Good night.